Okay, good afternoon, everybody. Thanks for coming. This is the first colloquium of the ECS colloquium of the semester. And so welcome, everybody. We're here every Wednesday at this time, and we get quite a variety of topics and speakers. Generally, we get very, very prominent, high-quality speakers. And today we start out with a very good first case. We actually have two speakers. We have Tony Yen. He's the Vice President and Head of Technology Development at ASML. I assume all of you who are here have heard of ASML and know the key role they play in the semiconductor industry. And Tony is currently, in addition to continuing in his role as a VP and Head of Technology Development at ASML, he is also serving as a visiting professor in our department. He will be teaching a course in the spring semester on the topic of today's talk. So if you're interested in this material, sign up for Tony's class. Tony was, he got his bachelor's degree from Purdue, his PhD and MBA from MIT. He worked at TI and at TSMC for quite a while before joining ASML. He's a fellow of IEEE and won a number of important awards. Tony's going to start out today, but he has a colleague here, Ron Goossens, also from ASML, who is a senior strategy manager at ASML. He's working part-time. He's partly retired. He is also an adjunct professor at Purdue, where he teaches. And he got educated in the Netherlands at Utrecht, and has been at Philips Research, Stanford, National, NXP, before joining ASML, where he leads computational lithography efforts. So they're going to do a tag team and tell us about EUV lithography, which is the hot thing now in microelectronics, and he'll give us the history and where we are and where we're going. So I'll start with Tony.
Thank you. Thank you, Jeff, for this very nice introduction. Is the microphone on? Yes, thank you. And Ronald and I were very happy to be here at Berkeley to give this colloquium. And without further ado, let me get started. Perhaps I'll get a little excited, so let me remove my jacket first, just in case.
Don't think you want to stand in the middle because you'll block the
No, I will be standing here. We want to tell you about EUV lithography. But I like to start with some history. But I like to start with the history of photolithography itself. Just give me 5 minutes, okay? Because this may be interesting to know if some of you do not know photolithography or are not familiar with this technology yet. So let me get started, right? It's the first part of the talk is the photolithography until early 1980s, and then EUV as a next generation technology, lithography technology, and developing EUV lithography for high volume production. Okay, so photolithography itself was invented in the mid-1950s by two groups. First was called the Bell Labs, where you folks were, and the second group was a U.S. Army's laboratory. So let me focus on the second group because the story was more dramatic. In the second group, the goal was to fit a proximity fuse into a mortar shell. Mortar shells are not very big. A proximity fuse is basically a cheap radar system. Okay. The goal is to have the bomb explode in the proximity of the target before hitting the target, right? To increase the probability of impact, okay? Because if it explodes right on target, you may miss the target. But if it explodes in the vicinity, then your chances are a lot higher of hitting the target. So this was the goal, to put the proximity fuse inside a mortar shell. Okay, mortar shell is very small. So in those days, the transistors were mesa transistors, germanium. Okay, how do you fit a mesa germanium transistor circuit inside a mortar shell? Well, these two guys, Jay Lathrop and James Knoll, from the laboratory, they thought of using, of course, they found out that the Kodak had a photoresist, and they thought of using a microscope, but operating in reverse. Okay, so this is a microscope, and this is where the transistor or a piece of germanium is, and they put the photomask here, where you would have the Polaroid camera, right? And you shine white light from the top. Now, what is this filter? Well, before the exposure, when you're aligning to the previous layer, you slide the red filter in there so that the photoresist is not exposed. Once you do the alignment, you take out the red filter, and then the exposure happens, right? You expose this, and then you get the transistor. And the transistor looked like this. The die is about 1 millimeter to 1 millimeter by 1 millimeter, and this is a mesa. The base size was not stated. The base contact, this little guy, one of these guys, is a base contact, is 0.1 millimeter by 0.25 millimeter. Nowadays, it's gigantic, but back in those days, it was hard to make. And then they also had to make the emitter contact, which is the other rectangle right here, okay? Same dimension. It was a success, and then what happened was that Jay Lathrop joined TI in 1958, and what happened in TI in 1958, Jack Kilby invented the integrated circuit, right? So Jay Lathrop worked at TI with Jack Kilby for the next 10 years. And where did the other guy go? Of course, he went to Fairchild, 1959, right, where Robert Noyce and others had invented the integrated circuit there. So, great story, and it's a bit romantic. So this was in the mid to late 1950s. And what happened next? What happened next is less romantic. Lithography in the 60s and the 70s, early 70s were mainly contact and proximity printing. Because those days, resolution wasn't really the top issue. The top issue is how to get these layers to align. So those machines were called aligners back then. And this is an aligner from Casper Instruments here in the US. These guys were the king back in the 60s, okay? They were very good at doing contact printing. You put the mask right on top of the wafer, right? You align, and then you shine the light. The problem with contact printing is that it generates particles in the space, or you're rubbing the wafer against the mask. So what happened was that later, well, we should create a gap between the mask and the wafer, and then they went from contact printing to proximity printing. Well, once proximity printing happens, Canon took over as the new king, right? This guy faded away, and then Canon made a much better machine for proximity printing. So this is the Canon machine until proximity printing was superseded by projection imaging, okay? And this happened in the early 70s, okay? So let me first give an example. Why did we go for projection imaging? Okay, so the example is, let's shine a lambda equal to 400 nanometer, UV light through a mask, imaging a slit. A slit is 4 micron, a wide slit, right? And the gap is 1 micron, 5 micron, and 10 microns. And this is the kind of aerial image that you get, okay? As you can see, that this is almost at the limit of the resolution, okay, of proximity printing. Because, why? Because you really cannot control the gap very well. If you can control the gap perfectly, then it's fine. But you can't, because first, well, the control itself, mechanism itself wasn't very good, but also the wafer is non-flat, right, is warped. So it's much better if you do it through a lens. And this is projection printing, same wavelength of light with a lens that is not very sophisticated, 0.2 NA, a very low numerical aperture lens, and this is what you get. If you're on focus, you're looking at the red curve, and if you're off by plus minus 5 microns, you're looking at the blue curve, right? So in one case, you're fighting diffraction. The other case, you're taking advantage of diffraction, of course, with the addition of a lens, okay? So this is what's going on in terms of physics. And then, of course, early 1970s, there was this company called Perkin-Elmer. They made the first commercially successful projection aligner. To be precise, in 1973. This was the Perkin-Elmer Microline, a 1x, meaning no magnification or demagnification, right? Reflective imaging system with an annular slit. It's actually quite clever. The designer of this optics was called Abe Offner, a gigantic figure in lens design. He's passed away. But this system has only 2 mirrors, concentric 2 mirrors, one concave, one convex, right? And the imaging is done through a slit. Why slit? Because Abe figured out that the optimal distance from the optical axis is this thing called H0. At H0 from the optical axis, the aberration was minimized, okay? Through a slit is fine because you can scan the whole thing because the mask and the wafer are actually GANed together through a shaft, which is not shown down here. So when the exposure happens, after alignment, you basically do this, right? You can never go wrong because they're together in one axis, okay? And this was the first, of course, then it became a hit. Thousands of these machines were sold, and the first one went to Texas Instruments for a price of $95,000. You cannot even get a mask with this kind of money, EUV mask, of course, right? So this was sold to TI, and then what happened? Intel 8888. Okay, this was not TI, this was Intel. The device size was 0.2 inch by 0.2 is about 5 millimeter by 5 millimeter device size. With contact printing, the yield of these microprocessors were only 20%. With microline, 60%. This basically, kept Moore's law alive back then, okay? And now, of course, this wasn't the end of the story. They were the king for a few years until the king is dead, and long live the king, the new king, of course. Who's the new king? Well, problem with the 1X Offner design was that it was a simple optical system. 2 mirrors, all spherical, both spherical. So the NA could not be made very high. The numerical aperture of the microline was 0.167, very low, okay? In order to get better resolution, you need to increase the numerical aperture. However, in order to do so on the Offner system, the aberration would become very high, okay? So we had to get away from this kind of a Offner design and to come back to the more traditional demagnified lens design. And this is what happened in the late 70s, early 80s. The first champion was GCA, okay? GCA made a G-line system called a 4800 man, right? And now I have to say a little bit about the resolution in projection lithography, okay? Only projection lithography, proximity lithography, the resolution formula is different. This is K1 lambda over NA, and this is minimum half pitch. We're just talking about this with Eli. Minimum half pitch, right, is a more accurate metric in our sense, because if you want to compare all the lithography systems, you don't want to compare with, oh, how thin the line you can print. It's always minimum half pitch, because with minimum half pitch, this K1 has a lower limit, which Ronald will talk about, 0.25. And then the minimum half pitch is lambda over NA. You can decrease lambda, or you can increase the numerical aperture. Numerical aperture is the sine of this half angle times n. N is the index of the medium surrounding this lens. Of course, this n is always 1 until you got to immersion lithography, right? At 193, then n became 1.44, okay? So this is what happened. And then, of course, later, KRF lithography with excimer laser, reliable excimer laser, became available. And then, of course, after that was the ARF excimer laser at 193, and immersion 193 with water 193, so the effective wavelength became 144, okay? And then, of course, we have EUV lithography. EUV lithography took a long time to develop. Why? Because in the early days, we did not think optical lithography could go beyond this. Why exactly this thing? This is called a point spread function, right? Because the NA is cut off here. So if you have a point source on a mask, object on a mask, you never get a point here. You get a diffraction limited point spread function, which is this spot, which is 1.22 lambda over NA. Okay. Now you can say that, okay, I can increase the numerical aperture, and I get a smaller spot. But no, not if you have lots of aberrations. If you increase the numerical aperture, then the spot won't get any smaller. This is the early days, exactly what we were facing, because we did not know how to make high NA optics without inducing a lot of aberration, okay, when we were here, okay? And this is when people started to work on NGL, next generation lithography technologies, and EUV was one of them, okay? So EUV development happened in the mid-1980s, and it went into high volume production in 2019, 35 years of development, okay? So let me now get into EUV lithography. The first paper on EUV lithography in the US happened in 1988. In 1987, a guy called Andy Hurlick, working at Lawrence Livermore Laboratory, back then was a laboratory that belonged to the University of California, here, okay? And he thought that, they had perfected, by then, the multi-layer mirrors to reflect soft X-ray light. Back then, EUV wasn't the name. Soft X-rays was the name for about the kind of wavelengths that's today EUV. And he published this paper. Of course, he said he proposed to use a reflecting mask instead of a transmission mask, because the reflecting mask, the mask substrate is also multi-layers, okay? And he proposed to use laser-produced plasma. Both of these concepts are adopted nowadays, okay? And of course, 1989, he and Nat Seglio and others actually, again, they went to the Three Beams meeting, and they showed a mask that they made, a multi-layer mask with gold absorber pattern. Of course, we don't use gold, but multi-layers were used, and here you go. See, the wavelength is about 13 nanometers. Today, we use 13.5. So this was actually the first paper in 1988 in the US. But in 1989, there was also a paper from a Japanese guy called Hiro Kinoshita. Kinoshita published a paper, look at this, soft X-ray reduction lithography using multi-layer mirrors, very direct. And he showed, this is his setup, a Schwarzschild optics with a reflecting mask, and these were the results. 0.5 micron lines and spaces from a 4 micron line and spaces mask, so it's a 8x reduction camera. The wavelength he used was 12.4, so he could not have used Mali psi multi-layers. It's a different multi-layer, okay? Because this is just below the absorption edge of silicon at 12.5. But this wasn't his first paper. His first paper was actually 3 years before, in 1986, published in Japanese, in Japan, at the Japan Applied Physics Society meeting, fall meeting, 1986. This was of course, the results were much cruder, but this was the first. So we normally regard Kinoshita-san as the inventor of EUV lithography, right? Although in the US, Andy Horelik was the first one. Okay. Andy actually told me that he did not know the results of Kinoshita, which I believe. This was published entirely in Japanese back in those days. It wasn't translated into English, but Kinoshita-san was the first one. But there was a third group, the Bell Labs folks. The Bell Labs folks, two people originally, Obert Wood and Bill Sylvast. They were working on a 37.5 sodium laser. They thought that, hey, you know, we could make this to do photolithography, such a small wavelengths. And they actually proposed at first the Offner type of optics. They want to coat the Offner optics with multi-layers and then use that to do lithography. Well, for some reason, that wasn't what the Bell Labs subsequently did. Subsequently, the results came from not the Offner optics, but the Schwarzschild optics. And Jeff Boker, right here, the second name, right? And you were heavily involved in this. This paper was published in 1990, and Schwarzschild optics at wavelengths of 14, very close to today's wavelengths, but they use the transmission mask. This is a membrane mask, okay, not the multi-layer mask. But look at the results, look at the results. Pitch equal to 100 nanometer. Back in those days, those were the best results. I was a student. I said, wow, you know. My advisor, Hank Smith, tried to downplay this. Oh, yeah, but they got a lot of aberrations. Oh, it doesn't matter, okay. Because to do this, they had to open up this NA. NA is, normally is 0.08. 0.08, if you put it into the formula, you couldn't get this, because this is on-axis illumination. Okay, so the smallest decay wind is 0.5. So in order to get this, they open up this aperture to 0.16. Okay, in order to get that, of course, that introduced a lot of aberrations, but that's okay. They published this, okay? Those were the best results. And then, in the mid-90s, Intel, led by Intel, Sunlin Cho, the chief technology guy at Intel those days, they formed this thing called the EUV LLC. And EUV LLC was formed, and then members joined, and those members were competitors of Intel. Nonetheless, they joined. They bought shares of EUV LLC at $5 million per share. AMD, IBM, Infineon, Micron, Motorola, they all joined, and Sematech joined, and then the money was pulled and farmed out to Virtual National Laboratory. Lawrence Livermore, Sandia, and Lawrence Berkeley, headed by Dave Atwood, right here. Okay, and this was the time when ASML joined EUV LLC. EUV LLC was critical, you know. Before EUV LLC, you might say, okay, we have disparate groups. They were gangsters. This is organized crime. Okay, a lot of IP, a lot of good work. But EUV LLC ramped down in 2002, 2003. However, when EUV LLC ramped down, ASML ramped up. In 2006, we shipped first 2 EUV machines. These called ADT Alpha Demo Tools. One went to Albany, right? The other one went to our partner, imec. And this picture was taken April of 2007. A tool was accepted in a year later. Of course, it took a long time to have this tool installed and debugged. And it used a discharge-produced plasma source, which we no longer use nowadays. So these were the first 2 tools. The pictures are from the second tool, okay, at imec. I don't have a picture of the Albany tool. And then, from that point onward, we developed 6 3100. These are the next generation beyond the ADT. 6 of them were developed and went to various companies. And my former company, TSMC, got the number 6 tool. Okay, the number 6 tool came to Taiwan. This picture was taken by me on the tarmac of the Taoyuan International Airport, summer of 1911. And then 4 months later, this was almost installed in our Fab 12 inside TSMC, Hsinchu R&D Fab. And now, how good could we do with this 0.25 micron R&D tool? This was a photo of the lowest metal layer with a pitch of 46 nanometers. This is after hard mask etch through, right? This was intended to be the design of 10 nanometer generation, but it did not happen. Look at this. This is a 2-dimensional design. In the end, the 10 nanometer was a 1D design because EUV could not make it, and then TSMC, we had to continue with immersion lithography, right? So we changed it to a self-aligned litho-etch process and a 1D design. But had EUV been ready, we would have continued with the 2D design. Okay, that's another story. Now I want to just give you a sneak preview. 11 years later, we could do this with the high NA EUV machine, right? Again, a 2D design, right? Now the NA is 0.55. This is from our first machine. You can see the pitch. The pitch was 46. The pitch is now 22. So that's progress. Again, this is etched into a hard mask. All right. So the EUV development at TSMC, this is a chronology of the EUV development at TSMC. Not only did we work with ASML very closely and tested EUV on 10 nanometer, 7 nanometer, 5 nanometer test layers, but we also had to participate in infrastructure development, right? imec, always been a member. We rejoined the Sematech, Berkeley lab, of course, the METs, and we also joined the ADAC in Japan to develop help develop the actinic mask blank inspector, and also there's co-funding of EUV development with ASML, to ASML, along with Intel and Samsung, okay? This was led by me, of course. Then in 2017, I left and joined ASML. In 2019, this is when EUV went into high volume production. As you can see, that this was a paper published by TSMC at IDM 2019, where they announced that the 7 nanometer plus node had been developed and used layers of EUV lithography. And of course, they also announced that next year that the 5 nanometer node will have more EUV layers. So this is first part of the story, okay? From the beginning to high volume manufacturing in 2019. So let me move on to the second part. Okay, last slide. This is what ASML did, right? Two alpha demo tools in 2006, and a bunch of 6 of them R&D tools in 2010, starting 2010. But in 2013, ASML did the 3rd generation, 3300B. The lens design is the same as the 3100, but the Germans thought that with better fabrication, they could enlarge the NA from 0.25 to 0.33. And this is the NA that we're using until now, okay? All the subsequent machines, 0.33 NA machines, all use the same lens design, sorry. And then 2019, we have the 3400C, the workhorse, and then all these machines have been retired, but the 3400C still working, and then to 2021, we came out with 3600D. Okay, now, that was the first part. The second part is the current status. First, the 0.33 NA, which is the workhorse, and then the 0.55 NA, the next generation high NA. Okay, so this is our latest 0.33 NA machine, the 3800, right? We've already gone through 3400, 3600, and now the 3800. The 3800 machine is quite a nice machine, and of course the throughput has been increased to 220 wafers per hour at 30 millijoules per centimeter square. You always have to specify the dose. If the dose is very high, of course the throughput comes down. We have a 500 watt EUV source now, and then we have a very low aberration projection optics here, okay? This is the 3800, and how did it do? Well, first let me show you some overlay number. This is a dedicated chuck overlay, meaning that the wafer gets on one chuck, and you expose it, and it gets on the same chuck, and you expose it again, and you measure the overlay. And this dedicated overlay number is extremely good, 0.5, 0.6 nanometer. I'm not talking about 1 point. Each field has 49 points, 76 fields per wafer times 12 wafers, okay? These numbers came from these many points. And this is not just the 3 sigma. It's mean plus minus 3 sigma. This is the whole thing, okay? And matched machine overlay, meaning that overlay read on 2 different machines. Okay, this one is not working. That's okay. On two different machines, but of the same type, both 3800. And then we get 0.9 and 0.8. Still very good. Okay, still very good. And you can see that we're below the spec. Okay, now, what's the reliability? I mean, are they all always down? No, they're mostly up. The availability is 93.5% worldwide on all the machines. This is the average availability. So it's already very good. Not as good as the deep UV machines. The deep UV machines, the availability is above 95%. So yes, we continue to work on it to improve the availability. And how many of these machines are there? Here's the cumulative number. By the end of Q4 2024, about 270 machines are in the field, all running, okay? 3400, 3600, 3800, these 3 types. The 3300s have been retired. About 270 machines by the end of last year, all working either in R&D or production. Okay, now, how many wafers can you produce a day? All these questions are asked by our customers. The number of wafers that we produce a day, on average, is about 3,000. On a single system, we can do a little better, right? So it's between 3,000 and 3,500. Of course, we're going to continue to improve this number. All right, so where are we going from here? Well, of course, scaling has slowed down, but it has not stopped. So scaling will continue, right? And because of that, we started to, okay, this is another thing. We're not scaling as steeply as before. This slope, this was the slope down to 3 nanometer generation. And you can see an inflection point, a kink, right? Starting from 3 nanometer, it comes down more gradually. We're never going to go back to this kind of a slope. However, we have not stopped, okay? This was really a turning point at that 3 nanometer generation. Because of that, 10 years ago, we started to develop a high NA system, 0.55 NA, because there is a need for scaling. Good thing that the slope has not stopped. Okay, so system design, 4 years. Module manufacturing started in 2018. In 2012, we integrated the modules. This is the source. This is the IF right here, intermediate focus. The scanner would be here, okay? This is the vessel, this is the illuminator. Picture of the illuminator made by Zeiss. That's the wafer stage we make in Veldhoven, Holland. The reticle stage made here in the US, Connecticut, Wilton, Connecticut. Okay, so you put all these things together, and we put together the first machine in 2023 in Veldhoven, okay? And then And then the next machine, I'll show you in the next slide. But then the next machine in Veldhoven is the machine for the joint lab with imec. Okay. But before this happened, we shipped a machine to our, okay, first let me talk about the optics. This is the biggest piece. This is the last mirror facing the wafer. This mirror has a diameter of 1 meter and an aberration number of 20 picometers. Okay, yeah, that's actually shown here. Okay. The first machine actually went to Intel right before the end of 2023. Of course, it takes a few 747s to ship the whole machine. This is just one of them. And it was going into Intel's R&D fab in Portland, Oregon. Unwrapping, cranes, as you can see, quite heavy. Okay, this is the frame. This is the illuminator, right here, okay. Yeah, well, this video came from Intel. And this is the end of the video. And you can see that the wafer stage is not in there yet. I don't know why they had this plastic thing to cover it up. The lens is already in there. The illuminator is not in there yet, okay? And the reticle stage on top is not in there yet, but the source is already in there, okay? So this picture tells a lot of story. This is inside Intel's R&D fab in Oregon. Okay. And then, of course, the next machine, we put it in Veldhoven. This is a joint lab with imec. Normally, a machine would go to imec, but this for the first machine, in order to maintain it more easily, we put it in Veldhoven, smack in the middle of our factory. And let me see, get the animation started. Yeah, this is real. The machine made it to a towel track, okay? And there's a metrology room with all the ancillary stuff is located. So this is the high NA lab we have at imec. And then the next few slides, I'll show results from this lab. First result is the DRAM, right? DRAMs, the most critical two layers in DRAMs are the hexagonal storage node lithography. Right now, the state of the art is right here. Page 34, okay? This has just entered HVM, high volume manufacturing, leading edge DRAM makers. You can see with pitch 34, low NA, high NA, low NA can still do it. In fact, it's done with low NA nowadays in manufacturing, okay? But high NA would have done it with ease. And then, of course, when you go beyond pitch 34, low NA, it'll become much more difficult. The equivalent dose would be very high. The reason is because you could not make use of the full illuminator, okay? You lose light. So equivalently, that means the dose is higher. With high NA, no problem. You go down to pitch 28 and below. This is the other layer. You know, there are two layers, right? One storage node, which is a positive tone, and then the negative tone is the storage node pad that sits underneath the storage node, the capacitors. Again, using low NA at pitch 32, very difficult, okay? With this thing is more difficult. The reason is that it has the periphery circuit, the subword driver, and the sense amplifiers in one shot. With high NA, very good. Right, ADI this is after etch, and even at pitch 28 after etch, it looks good. So high NA has got a lot of potential. It's not in HVM yet, but we hope that it will be HVM soon. Now this is logic, okay? Logic circuit, the hardest layer to print is metal 0. That's the lowest metal layer. Right now it's printed with low NA, 0.33 NA, with 2 or 3 multiple exposures, right? Purple is one, but brown's another one, and then you have these cut layers. If you were to expose it with high NA, you could do this in one shot. In the interest of time, I'm going to go through just to show you this result from imec, pitch equal to 19, which we're not there yet. Okay, we're at pitch 23 right now at the 3 nanometer node. Pitch 19 will be future node with the tip-to-tip. The tip-to-tip is another very important metric. This is single-shot EUV lithography. And not only can we do metal layers, but also the contact hole layers. These are 30 nanometer contact layers from center to center. So the nominal CD is 15. This is after lithography, and this is after etch. Okay, so, well, I mean, what can you do? How best can you do this? What's the limit of this? Well, I want to show you a slide that has a very small pitch. This is 8 nanometer half pitch, so 16 nanometer pitch. If you put it in the formula, the K1 is 0.33. Still, we're not close to K1 equal to 0.25. But you can see we could do it, but of course the image is of low contrast. All right? How do we, this cannot be in the manufacturing. The contrast has to be a lot higher. And how do we increase the contrast? And this will lead to the next part of the talk. I'd like to invite my colleague, Ronald. Thank you.
Tony, and remember that Tony talked about customers asking tough questions, right? Do you get good resolution, and can you make it cheaper? And that's ultimately the business that we're in. Better resolution. Tony talked about the formula that the minimum half pitch is K1 lambda over NA. So in general, try to go to shorter wavelengths. That's always very complicated for, to go from 193 to 13.5 was, what was the timeline? How many years did you say?
35 years.
35 years, right? So we're going to stick with 13.5 nanometers for quite a while. The next thing that you can do is go to a larger NA, but you already saw how expensive that is. And then you have the third factor, the K1. And I kind of feel a little bit pretentious being here, because then we start talking about computational lithography. And who am I daring to show up here at Berkeley, where one of your professors, Andy Neureuter, he's really the godfather of computational lithography. So I'm basically preaching to the choir, right? But allow me anyway to share my view on some of this. Obviously, we stand on the shoulders of many giants that have helped with developing a lot of the theory, all the way from Fresnel, Fourier, Maxwell, Helmholtz, Ernst Abbe there, this guy here, that was one of the first chief scientists of Zeiss, did a lot of work on microscopy and developed it from there. What did he say? He said in 1873 already, hey, the minimum pitch is half times the wavelength divided by the sine of that opening angle that we now call the NA, and he didn't have the refractive index yet. Now we say that n times the sine of that angle is the numerical aperture. But isn't it remarkable? Since 1873 to the day of today, a very simple formula has governed our roadmap. And the rest was simply technology. Well, technology is not always simple. Berlin from TSMC said, hey, lambda and NA, that's physics and that's geometry of your lenses, but that K1, that's all kind of illumination tricks, chemistry, resist contrast, aberrations, and mask tricks. And the minimum value that you can accomplish is 0.25. So I'm going to talk about what can we all do to reduce that K1. If we want to do that with computation, it starts with, I need to have a good model for what am I actually getting. So I need a forward model with which I can predict what is the quality of the imaging that I get. And that good model, that will involve a mask model. I need to see what is happening in my optics. What is the reaction of my resist? That's a lot of chemistry. And ultimately, I don't care what the pattern is of my resist. I want to have it in a device layer, so I need an etch model. That becomes my forward model. And a lot of effort has gone into how do I make that forward model as good as I can. And we continue to improve with that. more and more physics, more and more chemistry, and at some point in time we said, hey, AI is starting to take off, and perhaps when we have a lot of good measurements, we can develop an AI model that can predict what I will get, even without fully understanding why that is what I will get. And all of that is being employed. But once I have such a good model, I can go and play all kind of tricks. I can make a litho manufacturing check, where with the litho layer and the litho model that I have developed, I can now say, what am I going to get on the wafer, and is that what I wanted in the first place? Another option is that I say, hey, I have a litho layer, and I have measurements on what is the wafer. I can calibrate that litho model. Or I have a litho model. I know what I want on the wafer. What do I need to put on my reticle so that I get, in the end, what I wanted in the first place? And you contributed quite a bit of that. That's where the field of inverse lithography and so on. I'm going to talk about a different one today, and that's this one here. I know what I want on the wafer. How can I co-optimize what is the pattern that I put on the litho layer? And how do I instruct my scanner? What is the illumination that I will use on the scanner to maximize the contrast to get the best possible results? Now, when we talk about illumination, let me talk for a moment about an illumination system. Trick is, what I would like to have is very, very uniform illumination of my mask. And in order to play with interference and to play with diffraction and be able to manipulate exactly what is the interference pattern that I get on the wafer, I need to make sure that this is spatially coherent light. And how do we do that? We create this so-called 4F system. A guy, Kohler, invented this by having this 4-lens system. What I can create is, for every point in the light source, there is one particular set of planar waves that hits the mask. So if I imagine myself sitting on the mask, and I look back at the illumination, imagine a circle, and I could get light from that whole circle at me. That would be a cone of light. I could have light just coming from the center of that point. That would be one planar wave. I will also show you that I can have light coming from there and from there. And then I get very particular diffractions, and that's all the optimization that we're going to do. So here you see that a little bit. For every point in my source plane in the illumination, I now get a number, I get plane waves onto the mask. That leads to diffraction. So the diffraction orders are captured by the objective lens, and the bigger this lens, the bigger these opening angles, the more of these diffraction patterns I capture, and the better will be the reconstruction of the image here on the image plane. That's basically Fourier optics. So let's look a little bit more at that diffraction for those of you that are not totally familiar with that. Mr. Huygens already said, hey, when you have light hitting an opening, each point here starts to act as a source of spherical waves. And it's really the optical path length differences that then create this pattern here, where in some directions I end up getting light, and in other directions I do not get light. And those are called the diffraction orders. In essence, if I look at my aperture, the mask, and I think of that as a repeating pattern, I can take the Fourier transform of that pattern, and every diffraction order encodes one of the Fourier components. And you can think of the lens as a filter. How many of the Fourier components can I capture that help me reconstruct the pattern of the mask now on the wafer? So in certain directions, look at this wave go from this opening. This one here had this one was 1 wavelength to here. This one was 2. This one was 3. So in this particular direction, all of these waves are in phase, and they contribute to positive interference, and that is called the Bragg condition. Each of these diffraction patterns I can now project here in the pupil plane for the lens as a particular spot. And when these diffraction patterns start to fall outside the aperture of the lens, the numerical aperture of the lens, then no longer does it contribute to the image formation. At the wafer level, it basically looks like something like this. My 0th order, the light that straight goes through, these waves, they lead to no contrast here. The 1st order is a wave with the same frequency as the pattern. The 2nd order is triple the frequency, etc. So that's how, in the end, I reconstruct the image at the wafer plane. I'm going a little bit fast, so now, Abe was the one that said, aha, so now my challenge is, I know what I want as a wafer, as a light intensity on the wafer plane. My challenge is to optimize the source here so that for every source point, the waves hitting the mask with how they go through the lens and all the path length differences, how that all adds up to this spatial frequency on the mask. Let me show that to you much simpler. Here we have that one central point that I was talking about this large illumination disk, hitting a mask, creating diffraction patterns. Each of these diffraction patterns are within the pupil plane of the lens, and therefore they contribute to this interference pattern on the wafer. What happens now when I start to reduce the pitch? You see that some of the diffraction now moves further out. The contrast in my image starts to reduce, and I'm now at a CD basically of 0.5 lambda over NA. If I now go any further with shrinking, suddenly those outer points no longer are captured by the lens, and I have 0 contrast left. There's no imaging. But wait a minute, I can do some tricks, right? What if instead of using that point source, if I use a whole disk? Now you see that right here at the edge, there is again a little bit of overlap between the 0th order and the 1st order. So I start to see a little bit of the reconstruction of my image at the wafer plane. But the contrast is very low because there is a lot of light from the center that doesn't really contribute anything to the interference. So what if I could remove that light? That would improve my contrast, right? So I go and use what we call annular illumination. Instead of the light coming out of that whole disk, I now see it. If I look at from the mask back at the illumination, I would see it come from a ring, and I get much better contrast. Well, if I can do that, why not do even more? Because that light here at the edges is also not contributing, right? This is where the positive interference comes from. So let me remove that also. And I get even better contrast. Now I have something called dipole illumination. And that is what a lot of the fancy stuff that is happening nowadays, we can basically create with our illumination arbitrary shapes for the illumination, and what is the best illumination that will, for the set of patterns, lead to the best reconstruction. How does that then work out? If I have a full chip design, I will pick a bunch of critical patterns, the ones that I care about most. For those, I will start doing this optimization. I have a forward model. I keep calculating. I can use inverse lithography and try to do a more direct calculation. But in the end, I will end up with an illumination. You can see that there at the top. And with that illumination, I can, yeah, there you go. We start to improve, iterate on the illumination. And you can now start seeing that as I project, I get a cleaner and cleaner image. Once I have the very best illumination, I can say, okay, now let me use with this illumination OPC to improve the whole mask. And if I did the original selection of the patterns that I optimized for well, and those were really the most critical ones, then this illumination will actually work for the whole chip. So how does that optimization algorithm work? Basically, we tend to look at, hey, this is what the designer drew, this square thing. Now, we know that we can never print something square. There's always finite resolution. So if I would try to optimize directly to that square shape, my total cost function, which is all the errors added up, would be completely dominated by these corners, and that's artificial. So we say, you know, theoretically, the best that I can do is some target that I can draw here. Let me now try to get the mask and the illumination so that I get as close as possible to what I think is possible. And I want to do that for a range of conditions, not just for nominal, but also for a little bit more or less dose. Dose is never perfectly controlled. A little bit more, some focus variation, and the mask making is also not perfect. So I take all these variances into account and make sure that I arrive at something that is robust under these variations. Here is some of the math that I will skip. Here is some of the math that I will also skip that determines how all of that works. But what I wanted to point out here is there are actually two terms here. That is this here that captures some of the effects from non-chemically amplified resist. And I want right now to focus your attention here for a moment at this term, that this is a masked 3D effect. So what is a masked 3D effect? I'll go fast. I'm nearly done. Here is one of those poles of the illumination. The 0th order is light that goes through. It goes to my wafer. Here is the first diffraction order, and it goes here. Well, because of electromagnetic effects here, there is an extra phase difference between these two. That's called a masked 3D effect. And that means that instead of a really good reconstruction of all my Fourier components, imagine that I have a beautiful Fourier transform, but I'm a little bit off on the amplitude of some of these components, or I'm a little bit off on the phase of these components. That would start to affect your reconstruction. So our goal is to kind of reconstruct, how can I do that correctly? Because my one pole, remember the dipole illumination? This was one pole, and as a result of that phase difference, you actually get a shift in your mask. You see this phi A minus phi B? That phase difference leads to a shift in your mask. Instead of the intensity being focused around the ideal position, it is shifted a little bit. Now the other pole will have the shift in the other direction. So my total image is now the sum of two distributions. If they were perfectly aligned, I would have a nice sharp image, but they're not. So the image fades. I get a reduction in contrast. What could I do? Could I do something smart? What if I have the illumination, and instead of the dipole here, I move this pole down a little bit, I move this pole up a little bit, and in my lens, I can now compensate for the masked 3D effects, because this order here, yeah, these diffraction orders here, and here are the 0th order, and now I can have the one pole shift to the left, the other one a little bit to the right, and now they overlap again perfectly. Now that's simple if I only have to do with a 2D pattern. What we can now do, and that's why we have computers, I can actually generalize this, and I can take an arbitrary mask pattern for logic, and I can say, hey, what would now be the very best aberration pattern in my lens that would make that all these images from these poles overlap as well as possible? And that's what you see here. Here is what I just explained for a simple, if all I look at is lines and spaces, this is for the actual mask pattern here. And as a result, I get much better exposure latitude and much better depth of focus in my final imaging. So I hope that with that, I've given you a little bit of a flavor on how we can use computation to optimize the settings on the scanner, both from an illumination perspective as well as aberrations in the lens. We try to minimize the aberrations, and sometimes we introduce them on purpose to correct for masked 3D effects. Now, with all of that said, let me finish up the last part. just a slide on the roadmap and the outlook. Remember, the best possible resolution at the lowest possible price. So let's look at, we've looked at the best possible resolution, reduce the lambda, increase the NA, decrease K1. Let's now look for a moment at that cost of the technology, the productivity. The EUV light source, we've recently announced that. Our latest results in San Diego, we can get 1 kilowatt of power out of our dose. And remember what Tony said. In the beginning, we struggled to get 1 watt. Then at some point, we were really excited that we got 10 watts. TSMC told us that when we hit 80 watts, we can go into volume production. That was in 2019.
No, that was 250 watts.
Oh, that was yeah?
80 watt was 2014.
Was 214, okay, yeah, sorry. So that's when they said, okay, now we are serious about it. We think that you can get there. And by 2019, we were at 250 watts. We now have in our hands demonstrations that we can actually hit 1 kilowatt. Another way of reducing the cost of the system is by having more commonality between EUV, between the 0.33 NA system and the 0.55 NA system. So we have a roadmap on how we can create a more common platform that we will do that. With also an option to, in the future, start looking at 0.75 NA, for which we already have some prototype designs. And where we can get at the end, well, here is an example of with 13.5 nanometer EUV light from Paul Scherrer Institute, interferometric EUV lithography, where you do not have masked 3D effects. If we could really control everything, you can see that, yeah, there are already some evidence that half pitches of about 5 or 6 nanometer as an absolute theoretical maximum would be possible. So we still have quite a ways to go that we can scale more than where we are today. And with that, I come to the end, and I hope that I fulfilled my promise that I wouldn't be too long. Tony, why don't you join me for questions?
Hello. What happened? No, it's on. He was supposed to activate from back. All right. Oh, I think it's on now. Okay, so we'll take questions now for both speakers, and we're open for questions.
Do I understand correctly that if the end user cares about, let's say, resolution just along one axis, that's an easier problem from your perspective? Is that correct to say? Is that something that the end users are trying to, or you all collectively are trying to leverage?
Okay, so let's define first what the end user is, right? If the end user is Apple, then they tell TSMC it's your problem, right? TSMC will tell us, hey, do you have we want to use dipole illumination because that gives the very best contrast for one-dimensional patterns. Can you make a light source where all of the light only comes from these 2 points in that whole disk? Well, we can do that pretty well, but if you make these spots too small, we can only do that by throwing some of the light away. And if we throw some of the light away, then it goes at the expense of productivity. And so our newer illumination designs can use a much smaller, what we call a pupil fill ratio. What's the smallest fraction of that whole illumination disk that you can define that's where I want the light to come from and still use 100% of the light. So it's really a shared responsibility between us and the customer. But for every layer, metal 0, metal 1, metal 2, contact holes, vias, every layer has its own illumination. And let me take your example a little bit to an extreme. If I want the absolute smallest pitch in one direction, I would use a dipole with only 2 tiny little pieces of light here. I would now have great contrast in this direction and zero contrast in the other direction. So the only thing that I can now do is print lines that are infinitely long. Not a single designer is interested in that. So now what you could do as well, but if I have those very long lines, I will use a second exposure to cut them, but that's expensive. Perhaps bring in these poles a little bit, regain a little bit of that contrast, and now I can also print gaps in these lines, but how small I can get that gap, that's the so-called tip-to-tip difference. That depends on how you optimize the illumination and how you optimize the OPC. So it's a very interactive discussion between us and our customers. Hope that answers your question.
Okay. Here's another question.
Just a quick question. So, like, if the minimum pitch you're expecting is like not 90 nanometers, that does bring up the question: what exactly does the metric in like a node name refer to? Because it's clearly not the pitch of the features themselves.
Great question.
Yeah, so the node names, right? 5 nanometer node, 4 nanometer node, 3 nanometer node. Back in the days that we had the 45 nanometer node, that actually really represented the size of the lines. And at some point that became increasingly difficult, but people also became very creative in terms of, with design tricks and layout tricks, I can get more density out of the size that I have. So think of the 5 nanometer and the 4 nanometer and the 3 nanometer now more as an indication of what is the effective transistor density, how many transistors can I get per square millimeter or per square micron. It's more an indication of that instead of really the dimension. Tony, anything you would like to add?
Yeah, well, historically, Ronald was right, down to maybe 90 or 65 nanometers. That's the half pitch. When you say 65, the half pitch is 65. But nowadays, no, it's just a marketing name. I hope that this is not recorded. Don't want my customers to hear this is just a marketing.
They know.
Yeah, it's.
So cut this part out of the recording, okay?
No, it is an improvement over the previous generation. Yeah. But is it 2x the transistor density? No, those days are over. Okay.
So I'd like to ask a question about the optimization methods. Mm-hmm. So one of the great challenges in optimization is if you have a great many variables to optimize, it gets really quite hard. Now, you spoke mostly about the source optimization, and there's a lot of variables in the source optimization. Yeah. But then you also mentioned the so-called OPC, which is the mask optimization. Yeah. And that adds even more variables, because in principle, the geometric shapes can be represented by an infinite number of variables. Yep. So you have a very huge number of variables. So shouldn't you be doing the co-optimization of all of them together, rather than saying, I'm going to do source optimization? You should be saying, I'm going to do the optimization of everything. Yeah. The source, the mask, I do it all in one big optimization. Yeah.
So let me first answer that question. You're absolutely right, and perhaps I wasn't completely clear. Remember that video where we picked some clips out of this huge design, right? Those clips were supposed to be representative proxies for the incredible variety of patterns of the whole design. When we optimize the illumination, we co-optimize that with the OPC for those clips. And then but we cannot say, let's co-optimize the whole design with hundreds of billions of patterns together with all these variables in the illumination and with all of the variables in the projection optics. That simply computationally is not yet feasible. So what we do is we take some of these clips, there we co-optimize, then we say, now this illumination, probably since it is good for the most critical patterns, will be good for all of the other patterns, and then we do the OPC, a divide and conquer strategy.
Yeah, once the OPC stage, you don't change the design anymore.
I'm going to have to cut us off. I'm sorry, our AV support is going to leave us. Okay. We're well after time, but the speakers will stick around and happy to answer questions. Yes. one-on-one. So let's thank both speakers for a fascinating talk. And if you want to stick around, I think they'll be glad to answer further questions.
Absolutely.
Absolutely. How are you? Oh, I haven't seen you for a long time, yeah. So I'm doing fine. And then I understand that you are retired. Or not yet. Yes, yes.
I'm semi-retired.